Okay, I think we'll get started while more people filter in. So welcome back from break for our final panel of this day's events, entitled Public-Private Partnership Towards Fusion Power Plants. Our speakers here are selected and will outline the opportunities and challenges ahead for integrating fusion into the U.S. energy system. Our moderator for this panel is Professor Egemen Kolemen, Associate Professor of Mechanical and Aerospace Engineering, the Andlinger Center for Energy and the Environment, and Staff Research Physicist at Princeton Plasma Physics Lab, or PPPL. Eggy's research focuses on the application of dynamics and control theory to experimental plasma physics, primarily to address the challenges of fusion reactor design. He analyzes the dynamics of complex plasma phenomena using applied math and control theory with the aim of designing and implementing novel control techniques, which are then used to build real-time control systems from the ground up. Current research includes reduction of the heat flux to the fusion reactor vessel using advanced magnetic diverter configurations, detachment and radiation control, and disruption avoidance against instabilities such as neoclassical tearing modes and resistive wall modes. I don't know anything about that, and it sounds somewhat terrifying.
I should have given a better bio.
So please allow me and help me in welcoming Professor Egemen Kolemen.
Thank you very much. Thank you very much. So first, let me introduce our panelists here. You heard about me. We have Steve Cowley. Steve Cowley is the director of PPPL, Princeton Plasma Physics Laboratory, and he's a professor at the Astrophysics Science Department. And before coming here, he was at Oxford, University of Oxford, president of the Corpus Christi College, and before that, he was the executive officer of United Kingdom Atomic Agency Energy Authority. And he never likes to put it in on his bio, but he's a knighted sir as well. And we have Ahmed here. Ahmed Diallo is the program director for ARPA-E, working on advancing commercial fusion energy through pioneering research. He's also a researcher at Princeton Physics Laboratory, and he's the head of the Advanced Diagnostics Department Division. He's worked in all the continents in the world. He was born in Russia. He worked all around. He worked at Australian National University, at Swiss Plasma Center, and he has his PhD from University of Iowa. And he's an Oppenheimer Fellow, where he got to meet all the directors of national labs. And thank you for joining us.
Thank you.
And David Gates here. David Gates is the CTO's Chief Technology Officer for Thea Energy, previously known as Princeton Stellarators. Before starting at Thea, he was working partially at Andlinger Center and PPL, and he's one of the examples of startups starting from Andlinger Center. And he's going to talk about it, but his startup looks at a type of fusion reactor called stellarators. And at PPL, he was working on the stellarator design, and he worked on stellarators in Germany and Japan. And he worked, before PPL, he worked at UKE as well, in UK. And he's an APS fellow. Thank you very much for joining us. I'll give you a few minutes to introduce yourselves. Let's start with Steve.
Good afternoon. It's wonderful to be here. This is a very interesting time in the fusion program because as of last year, the Biden administration launched what they call the bold decadal vision of fusion. This is to try and put some electricity out on the grid by the end of the 2030s. This was stimulated by a National Academy report that said that would be, I think, a stretch goal, but a goal that was achievable for the fusion program at that time. So this is a shift from a program that's been really focused around, can we understand the science behind fusion systems, to actually getting one that will produce some electricity. Alongside that, we've seen in the last 5 years about $6 billion in venture capital investment in fusion startups. That's a phenomenal sum of money. One fusion startup, for instance, Commonwealth Fusion Systems at MIT, has raised, I think, $2.2 billion in order to actually make a fusion experiment, in fact, not actually a fusion reactor at that scale. These are phenomenal sums of money. And I think the drive behind pushing fusion forward is the kind of analysis we've seen from the Net Zero America group here in the Andlinger Center, which says that one of the holes we have in the future, and I did listen to what Amory said, one of the holes we have in the future really is options for firm energy sources, ones that can go alongside your renewable energy sources and switch on when the sun doesn't shine and the wind doesn't blow. And fusion would fill that gap really effectively if we can get it to work at a cost the consumer wants to pay. One last point. What the real advance, and in some sense the pull is that the need for a firm energy source. But the real advance that we've seen is that in my lifetime, and particularly in the last, say, 15 years, we've gone from having sort of empirical understanding of fusion systems. And for instance, in 1994 here in Princeton, we produced 10 million watts of fusion power in an experiment. And that was largely on the basis of empirical laws and understanding that was not very quantitative, to a point at which we can start to actually design fusion systems in virtual space. And there's a marvelous synergy with companies like Dave Gates' company, where we are essentially inventing in the virtual space new concepts that will make perhaps optimized reactor systems for fusion. It's that advance in the scientific understanding that's the big step forward, and not there have been good results, etc. But that, I think, is going to power the steps forward in the next 2 decades. So.
Thank you, Steve. Ahmed, do you want to introduce yourself?
Yeah, thank you. Thanks again for having me here. So I have started about a year ago as a program director of ARPA-E, and I'll talk to you a little bit about ARPA-E if you don't know about that. It's advanced research project agency that focuses on energy effectively. So it's basically similar to DARPA for the defense, but the customer for ARPA-E is actually the community, all of us here. And one of the main goals that ARPA-E is trying to target is to really kind of get target efficiency of all the energy systems, and then making sure they are sustainable, as well as trying to make sure that they can integrate in the grid. So we have to make the grid fairly resilient, and effectively also reduce import of energy. And so overall, my mission, or why I took this position at ARPA-E, was basically to enable technology for fusion, and that's my portfolio. So by technology, and Steve's talked about the bold decade of vision, which actually 2020s, we want to get net energy gain. The 2030s, roughly, what people have in mind is trying to get the pilot plant and the first of a kind fusion power plant, and then in 2040s, now throttle through to get commercially viable fusion, aggressively demonstration of fusion power plant. Now, what I do on every day, what I really want to challenge the community all the time is to come up with ways, enabling technology that's going to reduce the cost down the road. That's another thing that we really do at ARPA-E. We don't only look to get fusion by looking at the scientific part, but also making sure it's cost effective. So just to give you a sense, the first program at ARPA-E on fusion was called Alpha, and then there's Beta and Gamma that came. So basically it was looking at coming up with a cost-effective fusion device. Look at other concepts that are much smaller, that is not as expensive as ITER, for instance, see if we can kind of advance that. And then the following program that came out, ARPA-E, that focused on fusion, was also looking at partly on the energy, the net energy gain, but also everything that's outside, and we tend to call it the fire pit or the firehouse, effectively. And so one of the things that I'm tackling is the material. As you may or may not know, material that's facing fusion core, the neutron that comes out, they're going to be under extreme environment, and you need to come up with a material that's going to last long in a fusion power plant. So if you think a fusion power plant is about the design lifetime is usually 40 years, So you don't want to be able to, you don't want to change your material every day or so, because that's going to reduce your capacity factor. So what I'm pushing for is material. Can we design a novel material that's going to sustain the heat flux, the neutron, and not put some impurity in the plasma? So that's what I'm doing, as well as one thing that I would like to focus on is everything that heats the plasma, and we could talk about it later if you want. But that's all I have. Thank you.
Thank you, Ahmed. David?
Thank you. My name is David Gates. I'm the CTO of a company called Theia Energy. We used to be known as Princeton Stellarators. That was handy because people knew where we were from and what we made. So Theia is the Titan goddess of divine light and vision, and she gave birth to Helios, the sun. So we have, I think, a very poetic name in terms of, and all of my life I've been a fusion energy researcher. I actually started when I was 18 years old, and I kind of thought I always would be. I kind of thought I always would be such a academic researcher. In fact, if you'd asked me 5 years ago whether I would be spitting out a company, I would have probably said you're out of your mind. That, I have a really nice job. I work for Princeton University, one of, a very good employer. I think for many of you who work here realize that. And I just figured that I would do that for the rest of my life. But a series of events occurred that have changed the landscape in fusion. Steve alluded to the sort of the administration's view of fusion and how it fits into this bold decadal vision. That's a big thing that changed. He also mentioned, the amount of funding that has been available to private companies, which is, frankly, unprecedented in our field. That made a big difference. But also, there's a great deal going on in the world of philanthropy, because there's a bunch of institutions that have decided that we need baseload power, and want to try to convince researchers, not just me, but people like me, to explore a more rapid development for fusion energy, and then additionally, venture capital has sort of changed its mindset about investing in energy. I think the long-term timescales for large-scale energy development haven't always been in the realm of venture capital. And I've gotten a lot of help from venture capital. Some of them I think are in this room, actually. It's just really changed the landscape. And frankly, I was a pretty reluctant participant. It took a lot of people to convince me to give up my job for life. But it's been an amazing transition, frankly, and I'm really grateful that this has happened. The number of people have helped. Oh, ARPA-E, I left ARPA-E. ARPA-E was a big part of that transition. They have a tech to market program that helped me transition ideas out of a research program that we won a grant from ARPA-E, and they have this tech to market program is really, really influential. So I'm just, that's who I am, and that's why I'm here, and I'll spend a little time pitching my company, but for the most part, I just want to talk about the partnerships.
Thank you. I should have given a bit more background for people who don't know fusion. So our panel is composed of, we have government lab, and we have private partnership with the private companies. That's Ahmed is on that front, and we have Dave is here to talk about the private companies in a way. So we try to combine the private to public side and see how we can go forward with making fusion energy possible. I mean, for those of you who don't know, fusion energy is the main source of the energy in the universe. That's what stars make their energy. That's how all the energy, well, almost all the energy in the world is kind of because of the fusion from the sun. And it was not known we learned about this in the 1939 is the Bertha when it got this, that we learned that there's fusion happening in stars and planets that's producing the energy. And from there, and the first thing obviously we do when we find energy sources, we make bombs out of it. And that's what we did, the H-bomb, you probably know about that. And in Princeton, we had the Project Matterhorn, and maybe I should just throw it to you to talk maybe a couple of minutes about the PPL's history here, about how we went from the finding what fusion is to forming PPL. This is not, yeah.
I could talk for hours about the history of PPL because it's a very interesting thing, but in 1951, a professor of astrophysics here, Lyman Spitzer, got interested in whether you could control fusion reactions by holding fusion fuel at about 200 million degrees in a magnetic cage and get it to fuse and extract energy from that. And so we started the project here in Princeton in 1951 as a classified project, and it was declassified at the end of 1957. That's why they stuck us out over the other side of Route 1 so nobody would know we were there. They still don't know we're there. And the development from that time, we didn't understand plasma physics at that time. At 200 million degrees, matter is not a solid, a liquid, a gas. It's an ionized gas called a plasma. And so its behavior, we had to develop the science of plasmas in order to describe what was going on in these experiments. And our experiments went through a series of steps. It was in the 1970s that suddenly we went from under 10 million degrees up to over 100 million degrees in a decade, right? A factor of 10 increase in the temperature that we could confine. And this was the era of the tokamak. It was a symmetric donut-shaped magnetic cage, and it was here at Princeton that we suddenly made this big step forward. And that gave rise, during the oil shock, right, to the idea that we needed to build experiments that could actually do some fusion. Because that experiment didn't do any fusion in it, because we didn't put the fusion fuels in it. We just put deuterium, heavy hydrogen, and we should have put deuterium plus tritium in. And then in 1981-82, Princeton launched a machine called TFTR. And it was the first machine that was ever going to do deuterium and tritium in the same machine and actually do some fusion reactions. And in 1994, we set the world record, basically, at 10 million watts of fusion for 1 second. We were, at the time, putting in about 29 million watts into the device in order to keep it at what was then about 250 million degrees. And so we showed that it was possible to get the conditions of fusion. And at that time, there was then, we weren't in this state of people were, by this time, not all that worried about future energy sources. Certainly in Britain, we were pumping oil out of the North Sea as fast as we could. That record was then broken by the European machine JET in 1997, when JET did 16 million watts. And at that point, was injecting, you got 16 million watts out, you were injecting 24 million watts in, and again, it was for a very short amount of time. It wasn't until the experiment 2 years ago at Lawrence Livermore Lab, doing a different method, which is the explosion of small pellets with fusion fuel in it. They injected 2 megajoules of laser energy, and they got out 3 megajoules of fusion energy. So they actually got above what we call Q equals 1 at that point. The aim now is to get to a self-sustained fusion burn, where the fusion, you don't put any energy in at all. The fusion fuel just heats itself, and you burn, and you can add more fusion fuel and keep going. Nobody has ever really done that. And that is the next stage of where people are going. But this enthusiasm coming out of the private companies is to rush through that phase very, very quickly, and the science of that phase, in order to get very quickly to actually producing some electricity. Because there's a feeling that we really need to do this. And the White House is urging people on to make a sort of a bold step forward. Perhaps taking more risk than we would have if we just took it step by step by step through the science at that time. So we're in an interesting position. And of the companies, there's probably 4 that are funded at over sort of around $1 billion. and they will have enough money to maybe actually do some fusion work. There's other companies, and some of the more interesting ones like Dave's, that are funded at somewhat less and would hope to get up to that scale at some point. So it's an exciting time.
Yep. There are, I think, last time I checked, there's more than 50 startups in fusion area, and most of them are formed in the last few years. And there's billions of dollars being invested. That's on the private side. On the public side, there is ITER project. That's a big reactor that's being built in France, and that's supposed to produce Q-Constant, so it will put 50 megawatts of power and get out 500 megawatts of power. But that's a bit kind of delayed, and it's kind of a longer term, more like right now it's like 10, 15 years time frame. But private companies are going fast, or at least they want to go fast. So let's move on to our Q&A. So Dave, this is as a representative of the private companies, what are the issues you're facing as you're trying to ramp up in this fusion area?
Well, so first let me turn the question around a little bit. What's really been amazing is how well this has gone.
Okay.
And largely because I've just gotten a lot of help. And help from government laboratories, help from venture capital, help from the university, help from ARPA-E and the Fusion Energy Science Office, and help from also philanthropy. Actually, people have actually donated money to help me get this going. So the thing that's what really amazed me about this process is that people would actually come and urge me to quit my job, and Steve actually urged me to quit my job too. So just think about that, whether your boss asks you. But yeah, I mean, honestly, we're a startup. We have 20 employees now. We're hiring as fast as we can. We are raising money at a rate commensurate with our growth plan. We've had the advantage of actually sort of copying some of the more successful fusion startups. We actually did quite a bit of internet research on how they did it and what they did. It's really the same issues every other startup faces. We've got to get capital in place. We've got to get facilities. We've got to build we just built our first coil winding machine. That took a week, by the way. And we're now ordering one of the amazing things that's really happened is there's this high temperature superconducting tape, which if you ever build magnets, it's just amazing stuff. It's a 2 micron layer of superconductor that's 4 millimeters wide that carries 200 amps at 20 Tesla. It's a mind-boggling new technology that's out there that really, I personally think the real advantage there is that it's high temperature and that it's got this high current density. But it also has a very high ultimate field. And it's just changed the landscape in terms of designing fusion reactors. I can make a magnet this big that makes 10 Tesla on the axis relatively quickly. And the price is coming down very quickly as well. So, our challenges are really, I got to find talented people. I got to go out and, find engineers and scientists. Of course, all of the companies need people doing finance and operations as well, and we have to organize that. We have to create something out of nothing, and that's really just like any other business. The difference here is I have a very specific niche of people that are very hard to find. Experts in stellarator design. We have only got probably a couple handfuls of those in the entire country.
Well, he did hire one of my students.
Yes, I did, yes. He's actually doing very well. Yeah, that's true.
But I think, Dave, that one of the things you've sort of demurred on, and I think it's very important, this is based on the latest designs that are based on the latest science. Of all the startups, what you're looking at is based on this huge step forward we've taken because we have exascale computing and we have optimization rate techniques that come out of artificial intelligence and stuff in order to, optimize the design in the virtual space. So of all the companies, there are many companies that are sort of exploring old ideas and resurrecting old ideas. Of all the companies, yours is one of the very few that has a brand new idea.
I should point out that also there's a patent on that idea, which actually belongs to Princeton University. As a result, they have a fraction of us. So, I agree with you entirely. That's a very good point. And actually, there's not just exascale computing, but routinely available petascale computing, which, you just log in and run codes that, if you look back even, I think about what I did in grad school compared to now. I mean, we're taking things that are a factor of 1 million faster, or 10 million faster. And that, I look at, Daniel, Aggie's student, and he just thinks that's normal. So, they turn around these calculations that used to take us a year in minutes. And that's really changed the landscape of the entire
So in terms of the ramp up, so at some point, obviously, you'll end up needing, more inputs than you do now. So at that point, I mean, first of all, what do you think the private companies, private sector's role should be when we're ramping up to the billions or 10 billions, whatever those numbers are, to get to the path of fusion energy, production of electricity or hydrogen? How do you see the private sector side, and how do you see yourself kind of ramping up to that level?
So, public-private partnership, if you look at the history of, big scientific advances, effectively all the really important ones were public-private partnerships. There's the space, NASA is now turned into a true public-private partnership, but a lot of the work was done by government first, design work, and then there's the NASA COTS program, and that has really changed the face of the space industry, right? I mean, there is now a space industry that is independently creating spacecraft. Nuclear fission.
ERDP.
Yeah. So, I mean, you look at how that worked, that was a true public-private partnership. And it started in, actually that one, of course, started in military research. And then, when it transitioned to civilian production, there was a true partnership. And I think that's the model. I think the administration has really identified the NASA COTS model as the one it wants to follow. I think, role as a private company is you pick, you down select to something you're going to do. Then the government's role is say, is that a good idea, right? And then that's actually already happened. There was this first round of funding from the Milestone program. It's called the Milestone program. They actually have set it up so that you do the work on your own, and then they reimburse you when you're done. So that way there's no forward funding of things that don't happen. Yep. I think that's a great program. I think the way that's set up is really encouraging, and it's not very...
And that's a great segue to the person who's running the ARPA-E program. Is the manager who's not that exact program, but, can you tell us, Ahmed, so since you've led Infuse program, for those of you, you can explain a bit more about Infuse, what it is, and you're a leader in ARPA-E Fusion. Would you tell us, how you are helping, and what do you think going forward will be between private partnership, and is there any other programs that you're trying to bring in that you can tell us about?
So thank you. Yeah, so like Dave alluded to, so yes, we have Infuse that started 5 years ago, and that was basically, that comes out of the Fusion Energy Science program. And I was leading that here. It was co-leading with another director that is from Oak Ridge, who was looking at the technology.
Can you tell us what Infuse is?
Infuse stands for Innovating Network for Fusion Energy. So it's a program put together to really help a private company achieve their milestone in some way. So private company realized very clearly that the expertise lies at national lab and at universities, of fusion. National lab been doing a fusion for decades, so they want to start something new. They say, we realize, for example, there's an expert in, for example, magnet technology at one national lab. We want to tap the expertise, but we can't afford this expert. So the government basically just funds that expert to help the private company achieve their milestone. So as I was leading this, it was basically we look at the milestone of the company, and then we want to know to what extent by helping by funding the expert from national lab or university, how they can advance a milestone. And that was a metric for us. So that is going, and right now it funded about 72 projects at about $14 million. So the pot of money is limited. It's about $4 million per year, but it amounts to about $500,000 per project, and the performance period is about 1 year. Okay, so, and it's growing now because, we realize that it's expensive to fund national lab or university scientists to work on this. So it was targeted for expert at national lab only to advance the mission. So that's infused. Small amount of money, but it advances the mission. Now, ARPA-E on the other side, basically what we do, we are mandated by the Congress, where we focus on two main goals, is to enable to advance the energy technology to whole energy sector, so not only fusion, and to maintain U.S. leadership in advanced energy technology. Those are the main goals. And the way it works, we get about $500 million a year from the government, from the White House. And then there are programs that is about $30 million that are focused on metric. They are focus program. And I'm going to speak of the focus program that I'm interested in developing, and that is almost there, is to target material. Material, first of all, material is what I'm focusing on. So as Egi says, extreme environment, we want to make sure a material will last long in a fusion device, and more importantly, that it could remain ductile. By that, we mean that as you cycle your power down, irradiation tends to kind of make the material brittle, and you really want to make sure it stays brittle. And there advances in computation, like Steve was speaking about earlier, allows you now to kind of advance the material research. I mean, back in the days it was hard. Now we can do a little bit, we can cycle through some material. So that's one program that I would like to push forward as quickly as possible. The other advances that we need to look at as we move forward for fusion power plant would be to look at how you're going to heat this system. Okay? You want to heat to get to the temperature, the 100 million degrees, to get a fusion occurring. Now, in experimental, you probably don't care about efficiency. You say, okay, 20% efficient, good enough, as long as I have meet my target. However, to be commercially relevant, you really need to kind of increase the electricity that goes to the grid, and by reducing the electricity you need, and therefore to heat your system. So that means effectively you increase efficiency of your system. And that's another target of mine to see how do we do that. Those are long-term, because we have to do the research out to have people start thinking about novel way to do this, because for a long time we were focusing on just heating, getting net energy gain. We're still focusing on that, but now we have to pass that and say, where are we going? So those are the main programs I'm interested in, ARPA-E, and they all together are helping private company. And I try to, as much as possible, align myself with a bold decade of vision in the White House to make sure that we are focusing our energy, everything is coherent, and we do not duplicate with other agencies in a government. And so there's constant communication with the government, and that is actually is being done by Scott Shue, who was a former program director at ARPA-E, who's now the cross-cut lead at DOE, a senior advisor of Undersecretary of Innovation. So I think that helps so far, and I think it's very clear that the government is really wants to see fusion in a decadal time scale.
Ahmed, one thing that I've seen, the milestone program, this is one of the bigger programs that your ARPA was leading. The money might not be that much. I don't know, it's $50 million or something in the grand scheme of things, but all the private companies were very interested in getting it because you go through a very rigorous review of their projects, and once they get approval from you,
right,
all the investors are thinking, well, I'm not going to spend 1/10 the time they spend checking these. So can you tell about, in that fund, how you can help? And going forward, do you think there will be more like government directly funding these companies as opposed to just giving minor amount or buy the reactor from them directly? Do you see any of those type of things? Now you're working for government. I don't know if you can
So
say
I
these
can't
things
say
in a
much about-
hand-wavy way, but
No, I can't say that. But I mean, to your previous question, first of all, the milestone is not out of ARPA-E. It's out of DOE, Fusion Energy
but-
Science, to clarify things a little bit. However, the work, I mean, the people leading it mostly got a lot out of ARPA-E, where it's based on milestone. So we fix like strict metric, and we try to streamline the review. So that's something that actually it's benefiting the milestone program. And actually, it turns out 5 out of the 8 companies that got funded or awarded, I don't know if they got funded ultimately yet, but they're still awarded, still going through the process, are from our previous performer, ARPA-E. So that's good. And to Eggy's point, yes, investor like people that are funded by ARPA-E, because of the due diligence, technical diligence we go through. And so I think, anybody getting ARPA-E a grant, I think I'm not going to say that the guarantee to have fund from investor, but they really work hard at applying for these grants with ARPA-E. So yes, it's something that we all look forward to. And going forward, just to give you a sense, there are other program ARPA-E called Scale Up, where if you were awarded an ARPA-E program in previous years, you can apply to scale up your technology. And that is much larger pot of money. It's about $100 million effectively. And a few companies get that. And that's another layer of rigorous vetting, where they pull in also the investor to really listen to the performers as they pitch for the program to make sure that it has a viable path to go on the market.
Yep. And The Energy is one of the 8. So,
that's right.
We only get the best here. Steve, go to thinking about the position of public sector. So historically, national labs were leading these area. So things are changing now. It's in flux. I don't know how it's going to work out. But what do you think it's going to be, and what do you think it should be? Like, what is the best role for the national labs versus the companies? What would you like it to be?
Well, so I think we just talked about DOE is starting to see funding in fusion go partly through this milestone-based program, which is where the companies, in this case there were 8 companies who were awarded in the milestone-based program. And part of the milestone-based program at this point is to look at their technology roadmaps to deliver on this timescale of electricity by the end of the 2030s. And part of it is all of the proposals there had a public sector component of the public sector helping those 8 companies. So in fact, Princeton Plasma Physics Lab is helping 7 of the 8 companies, including Thea Energy here. And so this really is a public-private partnership. We're trying to use the best of what the public sector has, which is an immense base of knowledge in the science and engineering here to help people advance their ideas towards fusion. I would say this was very important to me as this was being set up, because there are a lot of companies. Some of them are bonkers, right? And they don't work at all, right? And you can do that on the back of the envelope. And you can say, yeah, and not necessarily low funding for some of the more bonkers companies. It's interesting to have a look at, how do people get money in this sector? Because we're quite far away from actually producing electricity in fusion. The TRL levels, the technology readiness levels of most of our technology are really low, right? We've got a lot of work to do to get there. So there's a lot of speculation that goes on in setting this. I think the size of money and something is because fusion is so, enticing as an energy source that we see the investment coming in. But what was really important was that the public sector not get into a situation where we are tied to ideas that really absolutely can't work. So this stage of the public-private partnership is to develop the technology roadmaps and to flesh out what we see along this line has to be done in order to get to that electricity in the end of the 2030s. And so 8 companies are at it, and some of them are laser fusion. There are 2 stellarator companies. There's a company doing, the one from MIT, doing a sort of conventional tokamak, which is very much the main line of research in the public sector. And then there are a couple of others in there. All these companies have, legitimate science and et cetera behind them and have been sort of vetted by the government. And I think for those companies, I think you just said this, part of this is having the government stamp of approval and so that investors can understand there's a lot of due diligence being done for these companies. And hopefully that will help them in their future investment and moving their concept forward. So I think we in the public sector are going to be helping them. I would say one more thing.
Building.
Right, one more thing. Getting the science right and being able to have a predictive set of tools that allow us to explore space in the future reduces the cost of developing fusion. You don't want lots of blind alleys in which we go up, we spend lots of money, and we find that, no, that won't work, right? So the mission we've been on actually since the mid-1990s, which is to try and nail down the science, right, has to be finished. And so there's a role for the public sector program, and that will go forward to really continue to develop the science and concepts there outside the sort of commercial goal that's there. And I think government recognizes that, and that we will continue at Princeton Plasma Physics Lab, developing the science.
Can I just follow that up real quick?
Yes.
So we have a couple of these Infuse Awards. And the primary thing, so one of them, what we did is we proposed to work with PPPL using a code that was written at PPPL. That really is there's a European version of a similar code. That solves magnetohydrodynamics as an evolution process. The number of people who can run those codes, you can count them on one hand, really, that are good at it. And, the idea that we would build a department within our company to do the same thing really doesn't make a lot of sense on a financial basis, right? But to be able to have the government, fund the lab to work with us really solved a whole problem for us. And it wasn't, national labs have overhead, but it's money quite well spent.
So, Steve, 2 follow-ups on. So, I just want to make sure I understand. So, you said you wanted national labs to focus on physics, but there's construction of power plants or test machines. What do you think the national lab should be doing for that? And one thing that's important is the regulation of fusion reactors, and how can national labs in that front. So this is maybe a tough question. I don't know. We can punt on that one.
I'm just looking out in the audience at Mike Ford, the head of engineering at PPL, and he's going to slay me after this.
Mike, join us, please.
He's absolutely right. The problem of getting fusion to work is not a science problem. It's a science and engineering problem. And in the end, if we develop a solution that costs too much and the electricity costs more than anything else, it won't be used, right? So we have to always be thinking, how do you make this thing? How do you make it cheaper? And part of our research is not science research, it's engineering research, and driving simpler solutions to these problems is what's going to get us to market. What we see, probably I'm saying too much right now, what we see with the route, which is the big international machine ITER, is the route that they're taking, which is sort of the main line to fusion, is too big and too costly to really ever get to commercial market. It'll be a great experiment. We'll learn a lot about what happens in a fusion reactor, but it isn't designed and on a route that naturally leads to, electricity at 10 cents a kilowatt hour, right? And if you're not going to make electricity at 10 cents a kilowatt hour, you can forget about coming into the market. So,
Thank you, Steve. I think we have 9 minutes left, right? That's correct. So, nope. Which one? Oh, we have lots of time. Okay, I was just, I'm just trying to. I see the clock going down. Okay, so we can continue with our discussion. Sorry for. So one thing I wanted to bring up there was the regulation front as well. So what do you think national labs should be? How can you help on the regulation front?
So there's been a lot of push, and the Nuclear Regulatory Commission has looked at sort of sketching out what regulation would look like for a fusion power plant. What we know is that the nuclear fission industry has somewhat been crippled by regulation that has made it really difficult to make money out of fission. And so trying to attract investors in without any certainty in the regulation market is going to be extraordinarily hard to do. So there's been an attempt to look at fusion, and we tend to say fusion is perfectly safe, it's, you know, it has no proliferation risk, and all these things which are not true. We have to be transparent. There is no such thing as perfectly safe, and there are issues about safety in fusion reactors, and there are issues about proliferation in fusion reactors, and we have to address those now and make sure that everybody understands in a very transparent way what we're going to do to mitigate any risks that come out of that. And so I think that this is going to be an iterative process between the public sector, the Nuclear Regulatory Commission, and probably the International Atomic Energy Authority, which we're talking to about these issues, and the private companies. Because the private companies in the end are going to have to deliver things that actually fit the regulatory environment. I don't personally think that you can nail down the regulation too much in a generic way. You can to a certain extent, but you can't really, until you have a design of a reactor, start saying, okay, what is the safety case for this reactor? What are the risks that we have to mitigate, and how are we ensuring, for instance, that, you know, there is no proliferation risk from this reactor? But I think it's good work that we're doing at the moment with the Nuclear Regulatory Commission to sort of sketch out what the issues would be, so that people, as they're thinking their ideas towards a reactor, don't go down a route that's hard to regulate. They actually try and design things that are easier to regulate, easier to get approved.
Ahmed, so there has been, fission reactors have been, you know, there was a couple of false starts maybe. I remember in the early 2000s there was funding from government to build big fission reactors, and that kind of was, you know, so successful. But then now there's a new push for small-scale fission reactors, and I think they're building it in Argonne Lab or something on national lab sites. So taking the fission as an example, what do you think the right path would be for government help on the fusion side? And is there any big long-term visions that you see happening at DOE?
Yeah, I can speak for ARPA-E, not so much for all DOE. I think I can tell you one thing is, what we should be focusing on now is, first of all, smaller reactor, so that, like you mentioned, we can service them quickly, just like the SMRs, if the SMR comes online. So, and one other thing that we have to think about is all the supply chain that and ARPA-E would like to look at it, that we can't overlook. We don't know where we're going to get all the part, all the tritium and all that. So all this thing needs to be thought through right now. So I wouldn't compare fission to fusion, and we try to definitely separate the two, because in fact there are safety issue concern, but at least it's inherently a little bit more safe than fission. And we have to admit that there's some issue we have to go through to NRC, and we're going through that. So all to just say that my personal view is like having a smaller reactor that you can deploy quickly and at scale, if we want to meet the 2040 aggressive scale of the bold decade of vision. So we have to start thinking now, as opposed to having a big system, smaller system that you can deploy quickly and massively.
Thanks. So Dave, I want to bring up, there's a lot of, obviously we're here, most of the discussions about climate change and how fast we can build things to help with this. And last time when we had the head of ITER, Bigo, and he said that I don't think it will be helping in the short term. The fusion will not be helping in the very short term, but in the long term we can see after 2050 is helping out. So when we talk to startups, generally the timelines are obviously much shorter than that. So what do you think is the right time frame? And do you think it's reasonable to see something shorter term than 2050, and why?
So timeframes. So we have, in private industry, we have aggressive timelines. We don't plan to do things slowly.
Yep.
We plan to do things quickly. Plans sometimes change. Anybody who's built something of scale knows that you don't control the outcomes. This part didn't get delivered. This part was out of spec. But I think, what you do is you create an optimistic timeline that's as fast as you could go, and you do your best to keep to that timeline. Like, this is just a philosophy of how to run a project. You don't set a timeline that's not aggressive, because if you're guaranteeing you won't go fast. So I think reasonable timeframes are, I think the 2030s is a reasonable timeframe for bringing electricity on the grid. There's a lot to do. As, Steve pointed out, there's a lot of technology to develop to make that plausible. In particular, we need to do heat extraction from tritium-producing blankets. We don't have a good handle on that. These are things that could happen in parallel, though, and that's the key. Is that we've been doing things in the fusion program in the U.S. in particular in a very serial kind of way. So we need to launch things on multiple fronts. Now there's risk in that approach, right? Because what if this parallel path doesn't really coincide with what we choose for our planned energy plant? So there's risk in that approach, because you might not coordinate them perfectly. But I think there's a sense of urgency that makes us want to take those risks. Yeah. Actually, this is something that I'm surprised how readily people accept this notion of risk in private industry compared to what I'm used to in the academic world. Governments tend to be risk averse. They want to make sure that if they appear to be supporting something, that it succeeds. Obviously for clear political reasons, right? Mm-hmm. I invested something that failed. I used your money. It's not a great sales pitch, right? So, but I think this is where private industry, we are only rewarded after we complete a task in this milestone program. I think that's the right model, I really am very optimistic that we'll do it in the time frame we're promising.
Okay, great. This is for most of you. I think most of you know this. So there are some technologies that we historically presume is going to be done by the national labs or governments, like tritium breeding, blankets. But now more and more I see companies that are they're coming out. They're not reactor companies, but they're engineering companies, fusion engineering. There's a bunch of names. And they say they claim to be able to do the subparts. So I'll throw it to Ahmed, because you seem very doubtful about this. So what do you think? Do you think how much of the technology development can be put on the private industry? All of it, or some of it has to be done by the government industry?
I think I just like to highlight, there are companies out there that want to do, for example, the fuel cycle or that you mentioned. That is very tricky to do for a single company. I mean, you need expertise that kind of are at the national lab. So having a partnership with national lab or people that have done that for other purposes would be nice. You have to learn from what people have done in the past. You want to repeat the same mistake. So I just believe in a partnership for that aspect. Some other technology that are not risky, with less proliferation issues, can be done by private company. They have the expert that move to a private company and they work on that technology, like the heating system, for instance, I can say, in material. But the fuel cycle and all that, it's not impossible, and I think it's challenging, but it would be nice if National Lab is really involved, because they have the know-how. You take, for example, Savannah River National Lab, they really know all about the tritium and all that, handling. So that's something you want to learn from an expert. I would say, tritium, and with all the hydrogen that's going on, there are some similarity, They're not the same. There's a similarity. So experts from Shell, all these companies that do hydrogen, for example, they can exchange, they can talk. So I can see partnership there too. But tritium is a beast on its own and requires a national lab expertise.
So it's very interesting. The President's budget this year reflected the bold decadal vision, and what it did was expand from about 720 million a year for fusion research to up just over $1 billion, $1.06 billion. And that expansion was to start to develop the technologies that you turn the fusion energy, which comes out basically as an energetic neutron, into electricity. All those technologies down the stream. This wasn't the best year to ask for a budget increase in Congress, as it turned out. And I don't think much of that will actually filter through this coming year. But I was encouraged talking to congressional staff in the Appropriations Committee that they were impressed that the President's budget followed some of the National Academy report and the community report that said, we need to start doing, somebody said it here, fusion serially and start doing fusion in a parallel sense, right? The logic came out of the 90s, which was, let's just do some fusion and get a fusion reactor working, and then we'll figure out the technologies of how to convert that into electricity and bring down the cost and all these kind of things. And the philosophy now with the bold decadal vision is we've got to do it, we've got to start developing those technologies, even though we haven't quite finished the job of actually getting the fusion reactor to work in a burning fashion, et cetera, because we want to do things in parallel. So I'm actually hoping that next year, we'll see what comes out of the President's budget now. Next year, we're going to see a bump up in the public sector funding, and a lot of that will go to industry, but a lot of it will go to developing these technologies you're talking about, Ahmed.
So do you think we'll change the name of our department, Fusion Energy Sciences, to something else that doesn't, that includes production of electricity? Fusion energy production, maybe? Okay, let's have some, thank you very much.
I was going to answer.
Ahmed, do you want
No, that's okay.
I'm not gonna. Okay, so now we'll have questions from you, and if you have a question, please do raise your hand. Let's start with any undergrads or grad students, if there are, raising their hands. Oh, there's a person. And then we'll go up in age, maybe.
So I'm glad you brought up the materials problem, and I think ARPA-E has been very proactive in that front. Like last year, you funded a project with Los Alamos on developing high entropy alloys. So I was wondering, in terms of high performance computing, how much of that is dedicated to materials discovery, or is it still like entirely or majority of it dedicated to plasma physics? And if you have time, can you comment on the 4 R&D centers that are dedicated to structural materials?
Well, okay, to the second one, I don't know about the R&D that dedicated structural material at the moment, but I could tell you a little bit about the HEA and the Los Alamos funding project. So mostly the material discovery, we do not control the computer time that they dedicated. So that's a fact. They have to apply for it separately. But we do rely, we want them to kind of work with the different agency, the other agency, to get runtime, to get like compute time. But I think what helped a lot in the material discovery is informatics, effectively. So machine learning and AI has kind of sped things a little bit up fast, and also the capability of doing high throughput experiment. That has gone a long way since we've talked about material discovery. So I give you an example. Over 1 year, that specific project was able to churn through about 1 million material composition, and they actually found 10 meeting some of the specs, that metric that they were put forward, that they were supposed to address. So there's progress, and there's a lot of examples like this actually in the past, I would say 5 to 10 years, out of other agencies. DARPA, for example, they discover new material out of GE that was able to sustain the high heat for missile defense, for example, for missiles in general. So you can think that informatics helps, computational does help. There's also I think out of Princeton there is OpenAI, I think, that is a code that's used for material discovery too. So to your point, I think it's not only compute time, but also being a little bit more innovative using machine learning and high throughput experimenters to validate the model that I have, that are reduced model at this point, and then ultimately one can do the full-on model, the FT calculation and so forth. That takes more computer time.
Thank you, Ahmed.
When I ran the UK program, we had a big computational materials group. But the missing piece in materials for fusion that the community has identified is we have never tested materials. So the neutron that comes out of fusion is a 14 megavolt neutron. The neutron that comes out of a fission reaction is usually between 1 and 2. So it's 10 times more energy. And so when it slams into a piece of material, it'll hit an iron nucleus in, say, steel. There's a recoil of it at 500 kilovolts of that iron nucleus, and it makes a little melt spot as you go through there, and it chips off helium, which makes bubbles in the material, because you get, and this happens in fission, but it happens in fusion in a different proportion, because that 14 MeV neutron, for instance, is much better at chipping off helium inside things. So we've done lots of computational stuff, but we've never tested materials in 14 MeV neutrons because we don't have a fusion reactor to test it in. So the proposal is, and they're building a big accelerator in Granada in southern Spain, beautiful place. Go if they invite you, because the Alhambra is one of the great wonders of the world. They're building a big accelerator to accelerate deuterium. They pass it through a curtain of lithium that strips off the neutron, and you can put a neutron spectrum, the right energies of the neutrons, on the material and test materials for these fusion neutrons and what the reaction of the materials will be to it. So the computation has been going pretty darn well, but we really do need to have some data, right? Because even though I'm a theorist, you don't trust them.
I should point out that as well as the Alhambra being one of the Rioja is also one of the wonders. It is my expectation that work will have to, to do materials research at that scale, commercial activity is improbable at best. And so the assumption I have, first off, if I damage a full wall of steel with neutrons, I'm going to retire, because that means we did it and it worked. But then, immediately after that, there has to be a solution for that problem. And that's got to come from massive research activity.
So Dave, how do you de-risk this when you talk to investors? Do you say, well, somebody else is going to find the materials? Let's talk about something else.
That's what I say. Yeah, that is exactly what I say. Okay. I say there's no way that I would expect them to fund, a materials research program through my company. I think.
You can really wind me up on this. Is that I actually think we have to, when the first designs of fusion reactors will have to have very easy replacement of the materials, because we won't know enough by the first, if we're going on this fast time scale, we won't know enough to be absolutely sure that the materials will survive very long. So we have to design something that is engineered to replace components very quickly and very easily, so that actually we can test the materials in situ in the first set of reactors. That's what we did in fission in the 1950s.
Yeah, right. Even the device that Steve's referred to in Spain tests a volume of material that's sort of a liter.
Yeah, it's tiny.
If you're generous, it's a liter. Yeah. And that's, you don't, that'll be very useful data, don't get me wrong. I think that's really crucial. But you don't build a battleship by testing a bolt. It's not how you do it. So you need to have a real-life device to test these materials.
But I am pressing this, and of course I'm not an engineer, and we have engineers in the audience, but I do think knowing some of the science and some of the material science will help us make choices, so that even though we're testing in the first set of reactors the materials in the wall, the program that Ahmed is running, and this testing device in Spain will mean that we're not flying blind, right? We may need quite a lot more data, but we're not flying blind. We're designing things that at least we think will last a few years in the reactor, right?
Thank you. Let's have another question. Thanks for the question. Hero?
An easy question.
Oh, okay.
Artificial intelligence. Obviously, you just relied a little bit, but has that sped up the process for you all, or?
Well, so there's been this big push, and it's really the last 5 years, of taking all these predictive models. And we, for instance, we calculate the turbulence. The middle of the device is at 150 million degrees, and the edges at 10,000 degrees. Sounds a lot, but it's 1 eV. That temperature gradient drives bubbling turbulence inside. Whenever you have a temperature gradient, you seem to have convection. And that bubbling turbulence is key to understanding how quickly heat gets out of the system and whether fusion can replace that heat quick enough. With that, we've incorporated this into codes to design magnetic bottles with fancy shapes. And Egemen has designed the best code in the world to actually calculate those shapes. And then we put these turbulent codes in with those shapes. He calculates lots of different shapes. We put the turbulence codes into that, and we start to do optimization, right? And we want to do optimization of the engineering too, because no point in designing a really fancy magnetic field that really confines the plasma really well, but it's horrible to build, right? We tried that once at the lab. So it's this sort of modern way of doing things that incorporates these AI tools with high-performance computing tools to sort of search through the parameter space. I think there are 10 billion configurations that people have been looking at.
So if I may, I'm the moderator, but if I can jump on that. We do some AI as well, but I think now AI ML is like being used for, it used to be that there was calls from the government to put something related to AI ML. Now there's regular calls and everyone is putting AI ML in it anyway because you need to kind of use that. And one thing that I work on, which might be useful for reactor, is there's a lot of decisions you need to make. There's like, many parameters that you need to check if everything is, there's an abnormality when you're running the reactor, everything is going okay. And if you try to write a human written code to do that, it just becomes ridiculous. And we're looking at using machine techniques to automate this. Is that a question or a comment? Oh, sorry, if it's a question, let's, 1 second. Yeah.
Yes, I actually had another question. Back to the materials.
Yep.
As you've said, of course, the materials for the reactor have to be extremely robust, handling heat, those normally high-energy neutrons, and in fact, also possible embrittlement from the hydrogen fuel itself.
Right.
One of the things. Down the line, can material spin-offs from these be used possibly to finance the industry, since it would create essentially enormously robust, resilient materials could be spun off for a variety of other applications, such as extreme chemical industrial applications, aerospace applications, or even, God forbid, military applications, such as hardening in a nuclear war environment, for instance. So the question is, yes, can these enormously high-performance materials, which will be necessitated for the reactor, be spun off to these myriad other highly demanding applications and be used down the line at some point, possibly to finance further development of nuclear fusion itself?
That's an interesting question. Yeah, thank you. I think I saw the other way around. So the fusion reaction material is really a multi-objective parameter scan. Right? I think it's a highly constrained one because you have the irradiation that comes in that really changes everything else. So I would say we've looked at material, for example, for the aviation industry, for turbine, for example, that are required to sustain like 1300 degrees C. We can use what they've learned there. We've taken, for example, material that is used for a nuclear warhead, for example, use the parameter scanned space of it. Combine this with one of the main requirements we have is erosion that plasma does, which is something that is not seen in other places necessarily. And then you want to make sure the material does not retain the fuel because you have tritium that really seeps through everything. And then you want to make sure, and you realize that with irradiation, you're going to have transmutation. As soon as you have transmutation of that material, not only you have this neutron flying in and then moving displacing a lattice, but you also have this transmutant inside that really would displace the lattice, and then something you cannot predict because there's no first principle code for neutron damage, right? So I like your question. I think if in the search of phase space of material, we find material that doesn't meet all the metric for fusion, yes, it's going to be put out there at the literature so people know what the performance of the material is, and then someone else can use it. But we also tap what research has been done in other fields separately where the dimensionality was much smaller to incorporate in the research. But that's a good question.
So right now, this is happening in other fields. For example, one thing is superconducting technology. Before fusion was a big deal, you had to know someone who knew someone to get a 1 meter superconducting. Now you can buy 10 kilometers. Now there's 12 companies as far as last I looked. So
10,000 kilometers.
10,000.
10,000 kilometers.
10,000 kilometers, yeah. You can go out and buy, sorry, I missed the order, 3 orders. But so this was almost all due to fusion. 99% of those superconducting materials is for fusion. But now that the prices are going down, it's available. There's many applications that maglevs and so forth, anything you can dream of. I think this is going to be like NASA always talks about we built man on the moon, but in the meanwhile we build the pen that you're using today or something. I think we can see that happening on other applications like this. I can list many of those. Last question.
Sorry. One more case in there. Obviously, when you're trying to do something really difficult, you develop techniques. And one of the techniques that, for instance, we developed in the UK was 3D printing refractory metals, right? It's not obvious. It's not a great, huge breakthrough, but there are lots of applications of 3D printing of refractory metals. And we spent a good deal of government money on developing those techniques, which companies now can use to do other things. 3D printing tungsten is a very interesting thing to do.
It seems to me, as a novice in fusion, that one of the toughest parts of it is the most mundane, namely how do you get the heat out and make it cost effectively into something useful like electricity. At least one of the startups claims rather prominently that it can do that without a steam cycle by somehow directly extracting energy from the charged particles. As a physicist, I don't understand their explanation of how they would do it. Do any of you think something like that is plausible, or are we stuck with steam cycles? Because if we are, then probably the technology is very uncompetitive with what it needs to compete with, which is not other thermal power plants. That's the wrong competitor.
Go ahead.
So it is feasible physically. You can do this. You can take electricity directly. But I'm not going to comment on that company and how they're planning to do it. That's a total different, Some of them are ridiculous. But it is theoretically possible. Technology is, not there yet, but it is, at least theoretically feasible. So I'll let you kind of continue with that.
So I would say that I think I do believe that it's not impossible. It is something we should look forward to. I mean, the steam cycle and all that, this is also something that bothered me when I started in fusion. It's like, no matter what we do, we're going to be using the same way of extracting energy than coal and all that. It is something that we really know, and we don't want to work too hard. I mean, we're working on supercritical CO2, which is very tricky, has its own challenges, and is going to benefit everyone. But the direct energy conversion is something that I feel like when we build like 1,000 of fusion power reactor, even though right now we think the challenges are too high to really do it now, but I think it's something we should probably continue to work at really steadily, because I would say that one of the issues that doesn't have for the neutronic, for example, with the charged particle, you won't have the neutron. So the material challenge becomes it lessens effectively. So some theorists would disagree with me because it's true, but I do believe that it is something we should not dismiss completely, because maybe we'll understand how it is.
So that company, and there are two actually, that I know of. There may be many more. The deuterium-tritium reaction is God's little joke because it's 100 times easier. The cross-section is 100 times bigger, basically, than any other reaction. But the energy, 4/5 of the energy comes out as a neutron. And you can't do anything with that neutron to do direct conversion. If you do a harder reaction like deuterium-deuterium, then, or particularly deuterium-helium-3, then that reaction, all of the energy comes out as charged particles. So you can do basically this. You can compress the plasma, fusion goes up, the pressure goes up, then it pushes out on the magnetic field. That induces an EMF around a loop. And when it goes out, it stops fusing, and then you push it back in again. And when it goes in again, it produces more fusion, and it pushes just like an internal combustion engine. Except you're extracting the energy because it's pushing the magnetic field out and changing the EMF through a loop. And so you can use this as a way to directly make electricity, and that's lovely, except you've got to do a much, much harder fusion reaction.
You're saying if you could get to, say, 100 million degree ignition, this could actually work as you describe, or is it just theoretical?
It's just theoretical at this point, yes. And it's not 100 million degrees for that reaction.
It's a billion.
That reaction is closer to a billion, yeah. Right.
So we work with 100 million. You have to go to billion to get there. Dave, what are you going to use? Water?
Yes.
Would you like some more water? Coffee, maybe?
So, I find on Earth that water is a pretty good coolant. That's the way I look at it.
Thank you. Well, thank you very much. Really enjoyed the conversation.
Thank you. Thank you all. That was our last session of the day, and I wanted to thank, once again, our moderator and panelists for making it such a lively and enlightening one. I hope today has been as educational and engrossing for you as it has been for me. Let me summarize a few of the things that I think we learned, or at least I learned. I'm going to take us back in time. We'll start right now, and we'll go back to the beginning of the day. We learned that with funding now coming from private sources and scale-up agencies such as ARPA-E, progress in fusion is poised for substantial acceleration. We also learned that we already know how to burn a fuel that contains 100% hydrogen without many issues, and that there is a large resource of it under our feet. But ammonia and hydrogen have potential environmental consequences that definitely have to be fully accounted for. We also learned that the path of CO2 molecules from cradle to final resting place really matters in a world that is going to try to sequester some of our past transgressions, and that we don't need to be particularly concerned about escape of CO2 even in seismically active areas. We learned that contributions from energy savings are significant, perhaps even dominant, and can be as simple as rerouting pipes and relocating and reducing the number of pumps. And finally, I was reminded how absolutely bad I am at Where's Waldo because I could not find either the car or the horse-drawn carriage. And finally, I'd like to, before we enjoy the reception outside, I'd like to thank all of our moderators and speakers who have come here from near and far and share their experience and expertise with us. So maybe a round of applause for them. And I'd like to thank the Andlinger Center staff, particularly Vivian Furman and Diana Dudash, who worked tirelessly to plan and execute this event, which I think went really well. Now, please join us in the lobby, or no, sorry, I think it's outside, just outside, for refreshments as well as poster awards. Thank you.
Thank you.